introduce the last speaker, I think.
I don't have the speaker's name stored in my head.
So the last speaker of the day is our invited speaker, Ashley Villar from Penn State University. Ashley, can you go ahead and share screen? And Ashley's going to tell us about the anomaly detection, search for anomalous astrophysics in the era of LSST. I'm going to make you full screen over here, which you are. We can't hear you. It looks like you're muted, though.
Yes, thank you. And I have a million screens. Hold on. I need to. Do you see my PowerPoint?
Yes, we see your slides. They look great, and we can hear you just fine. So.
Okay, excellent. And it's 47. Good. Okay. Yeah. Thanks so much for the invitation and for organizing such a great conference. I'm so sorry that I'm not attending in person. I unfortunately have long COVID, so my voice is mainly fine, but if you hear it make some funny noise, that might be what's happening. So I'm really excited to talk today about looking for anomalies in the area of LSST, which we've heard a ton about. And I think really this talk will be somewhat of a meta discussion about the problem at hand and how we can think about solving this search issue that we have by first defining what we even mean by anomalies in a mathematical sense, and then some of the solutions we're thinking about. So first, I just want to say the obvious, that time domain astrophysics is clearly a large span of possibilities, and it's stealing this really wonderful diagram from the LSST team. We all know this. As alerts come into LSST, they are labeled by many hardworking individuals who are sitting in the room, but we don't automatically know what the underlying physics actually is. For the sake of this conference, I think we're most interested in these terminal explosions I've highlighted here, the things which really are transient in the sense of they're aperiodic, they're short-lived. It's one shot to get an understanding of the underlying physics. And that, of course, includes things like supernovae, which is the dominating topic of most of this conference, but also things like tidal disruption events, galactic novae or cataclysmic variables, etc. And these offer a really unique challenge in the fact that they are short-lived and that we have to be able to identify interesting ones for follow-up in real time. And I really want to emphasize the problem that we are facing in the near future. So when LSST turns on, we all know this, it's going to be a drastic boost in the expected rate of transients. So one example that I just like to use are supernovae as some catch-all for it, where we know that right now, thanks to wide field surveys like ZTF, Atlas, etc., we find about 20,000 supernovae every year. And that has been the annual discovery rate for supernovae has been growing exponentially for the past few decades since the 80s. But LSST breaks exponential growth, which is absolutely wild. It'll have a step function of 2 orders of magnitude. And so in 2024, when it turns online, probably 2025, when it actually has a full reduction system in place, we'll find about 1 million supernovae every single year if we can correctly identify them. So I would optimistically estimate that thousands or so can get a single spectrum at one epoch taken. So that's a traditional label of the underlying physics. It's the best guess at what's happening. Okay, realistically, of those, optimistically, maybe 100 or so are going to be truly actively studied in real time. And by that, I mean high cadence spectroscopic observations that we can actually get a full understanding of the physics, multi-wavelength follow-up from X-ray through radio, and I think for most importance, having just human hours so that we can actually understand the physics, having a graduate student on the job long enough to write up a publication, probably about 100 or so per year. Okay, so just doing basic math, 100 divided by 1 million, We are facing the problem of having to choose 1 in 10,000 supernovae to study. So that's as if everyone in this room, and maybe tonight, this is a topic for over a beer, you have to pick 2 from the last year, and that's what we publish on. That's on a philosophical level, this level of importance that an object needs to be to our field in order to warrant follow-up efforts. That's wild to me. It's really a huge problem. And this is, I'm preaching to the choir, this is really the reason why I think at least, so many talks are about anomalies or finding something new, because it's not ridiculous to think if we have to limit ourselves to 1 in 10,000 levels of physics and 1 in 1 million levels of physics in theory is observable, we should maybe be expecting the unexpected and figure out how to actually identify that early enough to have a complete physical picture through our observations. So that's really the issue that's being tackled with this anomaly detection. And it begs the question, what is an anomaly? And there are a few statistical definitions. Luckily, the one that I think most of us are referring to and is probably of most interest are these out of distribution anomalies, which is what everyday language of anomaly actually means. It's this idea that we have some preconceived notions of what we should be observing. So in this cartoon, I have a really common observational space, actually was shown in the previous talk, where we have something like a measurement of how long a transient lasts versus how bright it is. And we can imagine that we have a pretty good sense of how this is populated through many, many observations of supernovae. And if something just doesn't look like anything else, so for example, something that's very bright and rapidly rising, maybe looks cow-like, my computer just loaded something, then we might immediately identify this as an anomaly. Statistically speaking, I can go and maybe say this a different way. We have a space that in this case is 2-dimensional. We might think of some algorithm that tries to estimate the density, the underlying density of events that we're only sparsely sampling from in our observations. And then we're asking the question, do I ever get a sample from part of space that I think actually intrinsically is quite low density? And I might think that that's therefore an interesting part of space. This is all fine and dandy way of thinking about the problem in 2 dimensions. However, as soon as we start adding more and more characteristics, so all right, I got duration, I have luminosity, but maybe I care about the underlying, the color at early times or the decline rate at 30 days after maximum. The more and more I add this, the higher dimensionality I get, and I start to suffer from what's called the curse of dimensionality. My density of sampled points gets tinier and tinier. And so now everything starts to look like an anomaly. So often we don't use these density techniques to search for out of distribution anomalies because our spaces are a little too big. And I think, as you've already seen again in a few talks, a really common strategy instead is to use something like an isolation forest as kind of a proxy to get around this problem. This has probably been explained, but I'll just explain it again since it'll come up later in the talk. The way an isolation forest works, it's made up of lots of isolation trees, where an isolation tree is a series of binary, so branching, very cute metaphor, decisions, where literally I just make a random cut in my observational space. So here, I'm just saying if duration is less than 10 days, you'll be on one side, and on greater than 10 days on the other. In higher dimensions, this would be a plane instead of a line. And then I take one part of that space and continue to bifurcate it according to those branches. And the idea is that I'll just keep going. The idea is that if you look really weird in this space, then I probably isolate you really quickly. So for example, my cow got isolated in just 2 cuts with this tree. But the higher density locations took many, many cuts to actually isolate it by itself. So in this sense, the anomaly score of an object, how weird it is inversely related to how many cuts of my trees it takes, how many cuts of my branches it takes to actually isolate you. And then it becomes a forest because I repeat this algorithm many times, because on just one random set of cuts, I might not get every object. I'm really not getting a statistical sense of how weird this cow is. And so we just put lots of trees together to make up a forest. But really the key takeaway is that if you are out of distribution, you take fewer cuts to be isolated. But there's other type of anomalies, and I really want to highlight that they will likely be of greater importance in a time of LSST. In particular, I think the one that's most relevant for us is the contextual anomaly. So this is something that isn't actually sitting in a low density part of our observed space. This catfish supernova is sitting just in between two classes, but otherwise kind of looks normal. And to put this in a more less cartoony context, here's an example of a catfish supernova. Oh my gosh, I think I just understood that pun actually. Okay, so this catfish is, I apologize, these are confusing plots. I'll break it down really quick. On the left-hand side, I'm showing a pretty old study now from Nathan Sanders, where it's again just this concept of, for one type of supernova, a type 2p or plateau. That's again the supernova type that comes from a big fluffy hydrogen-rich progenitor that hasn't lost its envelope. I'm plotting the duration of the plateau, well he is, versus a measurement of luminosity. In particular, what is the luminosity in the middle of the plateau time period? And this is just a collection of observations for that type of supernova for the Pan-STARRS Medium Deep Survey. Ignore all these lines, they're theoretical models. So here on the right, I'm showing you just one example. He is my catfish, where if I by eye measure the duration, it's about 120 days, that's where he is. And then, okay, at 50 days, post-explosion-ish, he's sitting around here. So he's not standing out really at all as a notable anomaly if this were the only two features I selected. However, with further study, which there's been a lot for this object, we actually realized very, very quickly that this was strange. And it's in fact a pretty famous now a very likely electron capture candidate. And this is coming from extended analysis of both high resolution spectroscopy, but also just understanding the late time evolution. So the key takeaway here is that this is a case of extraordinary physics that's hiding amongst the other observations. It looks to our eye not like an out of distribution anomaly, but in the context of its neighbors, it's in fact quite different. The way that we actually make a statement like that is to go through the scientific process and understand the underlying physics. Or a different way of thinking about this is that we put it in a different space. Instead of plotting it in observational space where we have durations or luminosities, we can plot it in an unseen physics space. So for example, I've fitted the model and I plot it in a radius versus ejecta-mass space. Or I say I did this, Daichi did this. And here now it's really clear that typical normal core collapse supernovae from type 2p do indeed live in a very different space than electron capture supernovae. In this space, we've transformed it into an out of distribution anomaly, which we have algorithms to search for. So the key point here is that if we change our space from the observed feature sets that we use into some unseen space that we think is more related to the physics, whether that be through physical modeling itself or just some transformation of the original space, then we are much more, we enable ourselves to actually look for physically interesting anomalies that don't otherwise stand out. One of the issues is that this can be a really complicated and nonlinear transformation. In other words, typically I have to fit a model, and that's really expensive to do. I don't know a priori how to go from duration and luminosity to something like the radius of the progenitor. And like I said, even if I do understand that, typically it's through the lens of a physical model, and I have to go through some process like running an MCMC sampler, going through many, many iterations of possible models to see which best fits the data. So it can be really expensive. So this is a lead up to just say that this is really what's motivating a lot of people to try to learn an easier way to go from observed space, which we can easily measure and understand, to an interesting and physically helpful latent space, something that we don't see, but we think is an underlying generative factor in the physics. So one solution that I will talk about, which is increasingly common, I think we've heard these words a few times, is to look for anomalies by learning a latent space, so an unseen transformation of my data, using a neural network. And we then hope that that latent space we've learned makes it a lot easier to look for interesting physical anomalies through simple out-of-distribution methods. So the way that we do that is, like I said, through a special type of neural network that I think has been brought up before, but I will just re-explain. I have been thinking a lot about using autoencoders for supernova light curves, where an autoencoder is just a neural net whose input is exactly the same as the output. In other words, I ask an algorithm to take my light curve of maybe hundreds of data points. In LST, it's more like 10 data points. And I tell it, okay, do whatever you have to do to give me back exactly the same light curve. That's a very not smart thing to do, it sounds like, because if I multiply my light curve by 1, I've totally accomplished the job at hand. I have returned the exact same function, but I haven't learned anything in the process. Most importantly, I have these large spaces, hundreds of light curves in different bands. And in fact, they're all different numbers of observations for each supernova. So I have no way to easily compare them to each other in observed space, unless I do things like measure durations or measure luminosities. So what I'm trying to do in essence is figure out, well, can I write down a model which only has a few free parameters to fully describe the light curve? So it's the same idea as what we do normally in physics, but instead of using physics, I'm going to use just a series of matrices and some nonlinear functions, those don't matter, matrices really, for a computer to figure out those physical equations for me. So the way the autoencoder works is it takes in the light curve, and then it must compress the data into smaller and smaller vector representations until it gets to a bottleneck layer where I tell it, you only have 10 free numbers, and that had better capture every bit of diversity you see in the population of supernovae. Just like when I look at type 1a light curves, I only have, let's say, 2 free parameters, like a magnitude and a duration. In this case, I'm saying you only have 10. And then you can go from those 10 numbers, and I'll let you go kind of back to the original space, have bigger and bigger representations, and at the end of that, give me back, to the best of your ability, my original light curve. So the key idea is that these encoding and decoding layers is what they're called, so not the bottleneck, represent the hard work of physicists that take years and years to write down the complicated formula. But then once we have the complicated formula, I only need a few parameters to actually write down the light curve for any type of supernova. That's the same idea. Once I have all these free parameters set, now every supernova that comes in, I can encode into a fixed vector of free parameters. They don't have physical meaning, to be very clear. It's just my computer coming up with some representation, and I've only told it one thing. Make sure that the thing that comes out looks like the thing that comes in. I haven't told it about physics at all. A really minor point is that I don't, there's a little extra fanciness to this, which is that it doesn't just, for every single light curve, it doesn't just learn one set of parameters. It technically learns a distribution, so it's probabilistic. So I learn, it's the equivalent to saying I learned the mass of a supernova and the error bar on it, except remember, it's not exactly physical. The second little bell and whistle that's added is we have a really fun and unique problem in LSST, which is that time domain astrophysics is actively making decisions in real time. Like I said, we need to identify these anomalies quickly and early. And so to do that, we just use a special type of neuron. So inside are all those matrix algebra equations that are happening. There's one extra step, which is that the matrix will have a memory of all of the information you've previously shown it for a given light curve. In other words, if I have two observations, my neural net will do its best to try to guess what the full supernova light curve looks like with that limited set of information. But as I get more data, it's able to seamlessly include that information to get better and better guesses of the best model vector. If all of that was too confusing, here's a picture. So I think this is much easier to understand. This is a real supernova. It's a type 1a because I know because we had a spectrum. These points are observations with error bars. You can see there's really only one observational point that's high enough signal to noise to be a real detection. And then these lines are actually showing what the neural net thinks the supernova will do, given the information we've shown it. So actually, given just really one data point, it's doing pretty bad. It thinks that this thing is maybe short and not very long lived. But just a few days later, with a few more colors, it actually picks up on the correct brightness that we expect for a type 1a, which is great. And then just after peak, it starts to pick up on important secondary characteristics of type 1a supernovae. So for example, we see this characteristic red bump in type 1a, so that's probably an opacity effect. And it seems to pick up on that. And then it's just the final estimate to show you with the complete data set, we kind of get the closest guess. So this is exactly what the autoencoder is trying to do. It says, I'm going to take the data, try to learn all the ways I can write down different models, figure out the best set of parameters to describe the model for this supernova. And what I'm able to do then is use that condensed model space, the latent space that it learns, to understand all of the supernovae and to look for anomalies. So this is an example of doing just that. Let me tell you some background information. So we did a study where we wanted to build an anomaly detection pipeline using the method I described. And for that, we cheated in a way, and we used the plastic simulated data set, which you've heard about in Elastic. I think you've heard about Elastic, which is the next iteration of plastic that I'm super excited for. But with Elastic, we were really lucky in that we got millions of LSST-like light curves, and they were all labeled exactly with the physics that was put in to make those light curves. And so we had the back of the book answer to physics that is rare and exciting and physics that isn't really interesting. And so we trained an autoencoder on all of these light curves. And with that, we created a latent space, so like this model space that we could put all of the light curves into. And this is an example of just one subspace of the full space. So I think the full space is like 10 dimensions, but this is just showing 2. And in that space, now you can see that really easily we can do something like train an isolation forest to say this guy is clearly far away from the cloud of all the other supernovae that we have. And so we're going to label him as an anomaly. And our hope, again, is that this space is more, it can bring out more physically interesting anomalies like that catfish that would be hidden in our observational spaces. I just want to highlight again, as kind of this aside, that probabilistic component. So I told you, like, oh, each supernova doesn't just get 1 point. It actually has an error bar in this space. There's a little bit extra funkiness that I'm not telling you about, which is just that I try to encourage all the supernovae to, as much as possible, fit themselves tightly into a little Gaussian that's centered on 0, 0. And if you can't fit in that Gaussian, you must be super weird. So this just helps encourage some of them to be anomalous. Okay, so doing that, like I said, with the plastic data set, you can check the back of the book and you can actually see how well you're doing. So in this cumulative distribution plot, I'm showing you different anomaly, the cumulative distribution of anomaly scores broken down by the various classes of mainly terminal events. We include AGN in this plot, but mainly things that go boom. So the takeaway, I realize this is really confusing plot, so let me just tell you what the takeaway is. We were happy to see that the really rare classes, like intermediate luminosity optical transients in red and superluminous transients in brown, tend to have higher anomaly scores on average, whereas really common physics, like type 1As, tend to have lower anomaly scores, indicating that our algorithm correctly pulls out rare physics as interesting and common physics as less interesting.
5 minutes, Ashley.
5 minutes. Oh yeah, okay, thank you. So let's just zoom into one. Oh no, I cut this off. This is a, okay, that's fine. This is just zooming into one example where this is an example of a superluminous supernova. It's like 1 to 2% of our sample, and it has a beautiful light curve. And one thing that we can do is, I actually want to show you the full thing. We can watch what our autoencoder, where it puts it in the large sample of all the supernovae as a function of time. And so in this plot, I'm showing you the opacity represents how far away we are from first date of observation. And so the darker it is, the further away in the light curve. And you can kind of see, so this is the blob of all supernovae. You can see that this guy kind of walks away from the blob. And what's happening is that his anomaly score is going higher and higher as the algorithm realizes that this thing looks pretty weird. And this middle plot is showing how these features in latent space evolve as a function of that same phase. And the coloring here shows us when the algorithm actually does decide that the anomaly score from the isolation force associated with this supernova goes to the top 1% of the most anomalous events in the sample. And what's really wonderful, and like what was cool about this, is that this particular object was highlighted as weird, worthwhile to trigger on well over a month before peak magnitude, which is you're all observers, I think, so we all know that's the ideal time to actually trigger on these things to get the underlying physics. So that was very exciting. It does seem like that this type of algorithm is successful in selecting interesting astrophysics. And I will say there were other tests that we did to ensure that it was also better than just selecting by observational properties. These are the ugliest plots I've ever made, so I might actually skip it. The key takeaway from these plots is just that the anomaly score we get, which derives from where is it sitting in this weird latent space we're making, it doesn't change much starting at max, and that's very helpful for us. That's what's being shown on the left, and what's being shown on the right is just that we checked a lot for understanding false positives. So when did type 1As get selected as weird and they actually aren't? And it turns out that luckily the false positive, so the 1As that we thought were weird but aren't, were selected well after max. So we likely wouldn't have triggered on them. Okay, I just want to take the last minute to make a couple like meta comments. Our latent space is physics unaware, so it's agnostic to the physics. In some ways, that's exactly what we want. By definition, unknown unknowns don't have a physical model, so ideally we would like to be sensitive to things we're not expecting. However, that's potentially not the best way to actually do this type of analysis. There is a lot of interesting physics that we can encode that we don't, that doesn't have to be exactly one physical model. So in our example, our neural net, like I said, it only knows one thing. Its only job, its objective function, is to make sure that my model looks like the data. That's how I trained it. And the latent space is just kind of it's a nice, it's a nice prize we get from this, but it doesn't explicitly know what to do with that latent space. It just knows it needs to use the latent space to solve this problem. But I'm allowed to include lots of other physics into this latent space. So for example, I could have an objective function that is the sum of something that minimizes the difference between the model and the data. And maybe it's something that for supernovae where I do know the physics, like I have a lot of labeled type 1As, those should probably look similar in the latent space I learn. And I can tell my neural net to do that through something called contrastive learning. And I know a lot about, many symmetries and invariances in my data. So one simple one that we're familiar with is like a redshift. We know exactly how redshift impacts the spectrum and the light curve of a supernova. And maybe we want all of the encoding, so the latent space, to be invariant to that. And there's, again, many ways to include this in a neural net. One example that's very general is just called group invariant neural nets. Super briefly, but I'm not going to do this justice. I just want to say that we tried some of these, including additional pieces of physics recently in another project, not for things that go boom, but for periodic variable stars, where we explicitly told the neural net that our data had periodic boundary conditions, and it really improved the ability for our neural net to find physically interesting anomalies. So this paper is on the archive and by a really wonderful incoming grad student, Leon, where we trained an autoencoder that's very similar to what I described before, but with periodic boundary conditions on a large sample of periodic variable stars from ZTF. And actually, these stars were, the stars that come out as anomalous in our learned latent space are a really unique set of stars that seem to be highly evolved, highly reddened, and so very dusty. And this is showing just that the sample that we pulled out from ZTF in Gaia, and it is a non-trivial selection of these extremely evolved stars. Okay, I think I'm over time, so I'll just leave up my key takeaways. Thank you.
Thank you, Ashley, for a very interesting talk. We have time for questions. Oh, let's take a question online. Kostya, over to you.
Hello, everyone. Hello, Ashley. Thank you for your talk. It was wonderful. And I wouldn't say anything wrong about autoencoder. They're very powerful, and your paper shown it. But I'd like to defend a bit isolation forest because I would say that usually people do not use large some sample size to build a single I tree. So you don't have very deep I trees in isolation forests usually. That's why you probably don't have these wide volumes, and it doesn't depend on how many features or how many samples you have to build your isolation forest. So it is the only thing I like to note. Thank you.
Yeah, no, that's really fair. I think maybe An isolation forest is still dependent on a linear combination of the inputted parameters. And so maybe one key takeaway to build off what you said is that we would just be limited by linear combinations of our observable parameters if we don't think outside of the box and think about more complicated features that can be extracted from these light curves.
Yes, sure. I absolutely agree with you. So here, autoencoders are very powerful, I think.
Yeah.
Great, thank you. We have a question. Was that a question or a stretch? A question. You do have a question, great.
Hi, Ashley. Wonderful work. This is Bhagya. So my question was with respect to the previous slide than this. So I know that's not your work, but has something like that been tested for supernovae? For example, so you find an anomaly for a live supernovae, and then you follow it up, and then you fill it with models so that it comes to some non-traditional parameter space. I'm just asking or curious if that's happened.
Yeah. So we are working, my grad student and I, Kaylee DeSoto, are working on implementation of an autoencoder to do just this. Patrick Alea is also working on an active anomaly detection algorithm, which I think uses observable feature space and an isolation forest. So I guess it's ongoing.
Oh, yeah. I mean, yeah. Thank you. Yeah, I was just asking.
Alex, question.
Hi, this is Alex Kim from Lawrence Berkeley Laboratory, and I had a question about the plot that you showed of the latent parameter space.
Like just,
the one
yeah.
where you showed the outline. Yeah, that one. And so this is made with a variational autoencoder. So you say that you try to make the distribution look Gaussian, and it's clearly non-Gaussian, but the transformations, the coordinate system is completely arbitrary. So I would imagine that there must be some transformation that can take those purple points and make them Gaussian. The metric is pretty much arbitrary. So what's preventing this from really looking like a Gaussian?
Yeah, that's such a great question. I actually love that. So training in random noise is essentially what largely prevents us from looking perfectly like a Gaussian. We can have these kind of extended features. How do I want to say this? The way that this works is that I can write down an objective function where that's all my neural net knows about. Is kind of like, I want to optimize one scalar. And in this case, it's two components. One is like a chi-squared, or it's just a residual. I want to make sure my outputted light curve looks just like the original. And then to that, I add what's called a regularization term, which is the KL divergence of this distribution and a normal Gaussian. And that KL divergence job is to say, to the best of your ability, you had better look like a normal Gaussian. And one way you can really enforce it is just by making that term much more weighted than the reconstruction term. So there's a slight trade-off. And the reason exactly why we do this is what you just said. There's an arbitrary rotation of this latent space. And so we want to ground it into kind of one basis set. And that's what the KL divergence is trying to do. I hope that answered your question.
I guess not quite. But
oh, no, I'm sorry.
I would imagine, I guess I'm, well, okay, that's okay. I can ask you offline.
Okay, I can answer on Slack.
Great. Well, we're now out of time, so let's thank our Ashley, our final speaker of the day, and in fact all speakers from this session and today. So thank you all.